Live streaming is on.
All right, so welcome everyone. We can begin now. So, Nitin, do introduce yourself and teach us what attention is all about.
Okay, so can you actually hear me?
It's a little faded.
Okay. Is it better now?
Yeah, it's better.
So let's fill the screen by
No, actually, it's not clear.
um,
It's in the left corner.
okay.
Yeah, we can see your screen. That is there.
Let me just try to fix it. Can you see it now?
Yeah, I can see now.
Okay. Okay, so guys, my name is Nitin. I'm also for. Excuse me.
It's in the left corner.
Still okay. Any better now?
Yeah, it's good.
Okay. Okay. So my name is Nitin. I am an engineering student, the last year engineering student at Model Engineering College. So in this series of our language modeling and translation, this is one of the most influential and the most important paper that's ever written for the entire field of NLP, I guess. So the paper has pretty obvious name. Attention is all you need. So pretty much the title itself gets our attention. Mostly, if you look at the entire literature, we can see that papers with such interesting titles always tend to be the seminal papers that ended to be stuck to the entire field for very long time. So this is such a paper. This has a lot of citations. I think more than 1,000 citations. A lot of the language models in the later structures we see, like the BERT structure or the GPT-3 structures. They're all based on these ideas that this paper, the attention is all you need, is present. So the paper was jointly written by some researchers in Google Brain team around in the year 2017. So if you see this paper cited somewhere, you should see this name, Vaswani. So you should see the citation as Vaswani et al. At 2017. That is going to be the citation of this paper. So let's go with the presentation first. I guess you can see the presentation clearly. Is it clear?
Yeah, it's clear.
Okay. So as you might see, this is the transformers, and attention is all you need is a discussion text. So we can start with some background ideas. I think these topics were already covered in the first session, but we should actually just revisit them just for the sake of completion. So we have to actually deal with the in the entire the paper, attention is all you need is going to deal with translation. So translation, as you might know, is a sequence to sequence model. A sequence to sequence model in the sense, I mean, you take a sequence in one language and you transfer it into a sequence in another language. So it would be good if we understand what exactly a sequence data looks like. So let's just take some examples of the kind of sequential problems that we usually experience. So the first one, as you can see, is a speech recognition problem. The speech recognition problem has been one of the long-standing problems in the entire field, and pretty much everyone knows the speech recognition problem. What you have as the input is a time series. These are the wave representation of your audio, and this is a sequence. And this sequence is transferred, or the model trains on this sequence to finally understand what the speaker is trying to speak. So, for example, this sequence output. Hello, can you hear me? Hello.
Yeah, you are audible.
Okay. I try to blend it. So, speech recognition runs this problem where our input is a sequence and the output is another sequence. Where our input sequence is an audio sequence and the output is the language sequence. Another one is music generation problem, but we may or may not have an input. That's why we have the phi here, or the null input is here. And finally, we get a music transcription on the right side as the output. That's a music generation problem. If you go online into let me see, something like Jukebox, you might understand some idea about the kind of state-of-art models that we have in music generation. If you don't know Jukebox yet, you can go and take a look at the Jukebox. Here it is. So these structures and all these structures that use the sequences that attain the state-of-art models, in some way they use all the ideas that this paper is going to present. So that's one problem, music generation. The other one is sentiment classification. I think a lot of people start with sentiment classification while they do NLP programming. So the basic idea is you just give as input a sequence of words or sentences. So it's like there is nothing to like in this movie, which is actually a bad review. So all you have to understand, the model has to understand that this is a negative review of the movie. So we get a sequence of input and we get a discrete output. That's here we have 1 out of 5 stars, which means this is pretty bad review. Another one is the DNA sequence analysis is one of the another influential application of sequence to sequence models in which we are transcoding the DNA sequences. Also, the obvious one, machine translation. We are going to talk a lot about machine translation in the entire presentation. And the last one is video activity recognition. So if you have some idea about CNN, then you know how the basic computer vision work and all the state-of-art models work. But still, other than images, if you look at videos can be considered as sequences of images. So we have to look at the sequences of images to finally understand what exactly maybe the person is doing. In this case, this is saying, well, running. So we get the output as running. So what I had to emphasize with this slide is that the kind of problems will vary much different in the sequence world. So in the first case, as you can see, you get a sequential input and you get a sequential output. In the second one, you have no input, but you generate a sequential output. In the third one, you get a sequential input and a discrete output. So these are the various kinds of ways in which all these sequential problems in our field would look like. So based on this, we can classify the sequence models into based on the inputs and outputs that are in our structures. So first one is one-to-one model. It's basically just like any other neural network model. So you have one discrete input and you have one discrete output. So just like, let's say you have you're building a classifier for let's say an image classifier. So you give a dog picture input and you get the dog picture out. You get the classification as it's a dog. So that's like a one-to-one mapping. The second one kind of model we see is the one-to-many model. So one-to-many model is something like let's say this can be considered a one-to-many model. The music generation problem. So you can actually maybe give no input, or you can give the input, the genre of the input. So let's say I want to create a rock music. So that's my input. It's something like discrete input. And you get a sequential output, which is one to many output. The other one is many to one output, as in the sentiment classification case, in which we will create the input as the sequence, which is a many input, and you get one output, which is a discrete output in this case. So there are two classes of many-to-many models that we deal with in the sequence model world. So there are two ways in which you can handle the many-to-many model. If you look at the one-to-one model, you know that there is this unit that does all the work here. So you give input to it, and you get output right out of this unit. In the one-to-many model, we are seeing that you give input here, and you get output out of each of these units. In the many-to-one model also, you can see that you give input to all these units, and you only get the output from the last unit here. But in the many-to-many model, we have basically two ways in which we can actually model these structures. The first model is shown to the left side here. So what this model does is each unit takes an input and it produces an output. So takes an input, produces an output, takes an input, produces an output. So this is the first kind of structure we can see. But one peculiarity of this model, if you just take an observation here, is that the dimension of the input and the dimension of output has to be same. So let's say I have a 5-word sentence here. My output should also be a 5-word sentence. So that is a peculiarity of the left side model here. That's a many-to-many model in which each unit takes an input, each unit generates an output. Now, there's another way in which we can model the many-to-many sequence structures. In this case, we just took the input and made the output. But in this case, what we do is we take the input and we just keep them in our memory, or we just make some representations of these inputs in our memory until to a final point where we have the representation of this entire sequence. So for example, in our case, which is the machine translation. So if I give the translation that I visited Africa in September. So when I say that sentence, this sentence goes here, and each of these words go in one by one into the units, which could be any units. We could say it is an RNN unit or CNN unit. Let's just say it's some kind of deep neural network structures here. So this input goes into each of these units. So in September, I went to Africa would be the model. And the model will actually, at the end of reading the sequence, it will generate a representation of this sentence. It's something like a sentence embedding, but we'll look at it deep in later slides. So in this many-to-many model, we will have this representation at this intermediate stage. Then we will generate the output with a similar structure like this one. So in these cases, you don't really have the inputs here, but instead you generate the outputs based on the intermediate representation that we create here. So these are the kinds of sequential models that we experience in all our fields. So you understood the sequence data and the sequence models. Now let's look at our problem. That the problem we need to discuss here is a neural machine translation. So if you have some experience with machine translation, or if you have took some course on natural language processing, you are already familiar with the machine translation. But it's very possible that you learned about the statistical machine translation. If you're under K2, then probably you have this NLP course as an elective, and we are going to learn the statistical machine translation in that course. So the statistical machine translation would, let's say, it creates a probability distribution of the language, It uses the phrase-based translation. So for a given phrase in English, I would generate a given phrase, a translation phrase in German or French or whatever target language I would need. So that is statistical machine translation. You might be familiar with the term, the hidden Markov models and all such models. So they all come under the idea of statistical machine translation and language models. So the neural machine translation was pretty much a new, I can say new, but it's pretty new compared to the statistical machine translation. This neural machine translation, our aim is to train a neural network to do this machine translation. Instead of the phrase-based statistical machine translation, in which we have to hand train or hand tune every phrases by focusing on each of them, what we do is we train a large neural network to do this translation for us. So that's the field of neural and machine translation, and I think it started in around 2013, I guess. It is this paper. I'll share this link to this presentation shortly, so you can go to this paper. I have added the link here. So this paper, you will discuss about a translation model, one of the first translation models that use neural networks. It's going to use RNN. We are going to discuss about RNN shortly. So these are the important papers that's going to be the most important, influential in the neural machine translation field. Okay. So I'm going to talk about the RNNs shortly. So we already have some idea about RNNs from our first few sessions. So the RNNs is nothing but we have seen all those sequential kind of data, like it can be music, it can be any kind of other audio or the textual input or anything like that. So what we do is instead of giving this sequence to let's say an CNN model, which is a convolutional neural network. This is another deep neural network. If you don't know about CNN, it doesn't really matter. So we give the sequence and we get, let's say we have a sequence output.
Your audio is breaking. Like,
Excuse me?
your audio is breaking.
Audio breaking, okay.
I think it's all right for me. Let's see.
Okay, let me continue. Okay, so in this structure, we are actually just. So I think I have one already here, so I just use it. Okay, so I guess you can all see this structure. So let's just say sequence model, we talked about the sequential kind of data. So instead of using some deep neural network like CNN, we are going to use a special kind of deep neural network, or let's just say a neural network called the recurrent neural network. What the recurrent neural network are very famous for is their ability to handle the sequential data. So sequential data like the audio data or the textual input. So what we have here is a single RNN unit. So what the RNN unit will do is that, let's just say our input is let's just say we have the input as okay, sorry. Let's just say I have the input, I am a student. So when I give this input, if I'm going to deal with something like a CNN, then you must be familiar with, you must give this entire sentence into, you must make this entire sentence into one large matrix, which you will then pass into the neural network, which will then make a classification or make a new sequence or something like that out of it. But in the literature, if you look at those papers, you will see why they are not really successful in doing this. So that's how these RNNs came into existence. So they are built to handle the sequential data. So if I give this input, I am a student, which have 4 words, so it's going to go as inputs like this. X1 would be I, X2 will be I am, then the next one would be A, and the last one would be student. The XT would be student. So you give this input in a time sequence. What I mean by a time sequence is that instead of a CNN which looks at instead of a CNN, or let's just say any other neural network or another models which might look at the entire sequence just as it is, we are going to break down this sentence into a sequence. The sequence of I am a student has 4 words, which makes a sequence. So each RNN unit is going to take exactly one input at a given time. So you take I at this point. What do I write? So let's just say I take the input as here. I will take the input I. What I'm going to do is, first of all, I'm going to initialize some activation vector here. This is probably is going to be a 0 vector. And I'm going to use some kind of function here inside this. I'm going to use some kind of function which will use this value I and this activation value, which is initially 0. We will use these values to compute 2 things. In this case, 2 things. So you're going to compute a new activation value and an output vector here. Which output vector is clearly optional. You can either include it or you can exclude it. Doesn't really make a difference based on what your application is. So in this case, we are using these 2 inputs, and you generate this new activation function. In literature and probably all those blogs and videos you might see, you could hear the term hidden state. Hidden state is also a word you can use instead of this activation. So instead of this A, you might see an H0 coming inside and an X1 coming inside. So the H0 and X1 might create a new hidden state of the unit. So this happens in one time slot. This entire operation where you take the activation and input and crunch it into a new hidden state, this happens in 1 unit. So similarly, you do for the next word here. So in this case, let's say nothing is outputted here. So let's just go with the next sentence, next word here. So here you're going to give X2 would be, let's say it's going to be M. So this input M is here, and here you're going to use the activation A1. You might remember that the activation A0 was probably initialized to a 0 vector, and these were together creating the A1 activation. So essentially, you could say that the A1 activation knows something about the previous word. So A1 knows something about I. So that's the whole idea behind this. So A1 knows something about I. And this is going to be used along with the second word in our sentence, which is am. So the RNN basically gets the sense that we are talking about I am. So that's coming from the activation and the input we have. So similarly, it's going to use these 2 to create the new activation value. In this case, it's going to be A2. Or if you like to call it the hidden state, then the new hidden state, which could be H2. So this H2 value is going to have the idea about both I and am. So H2 know that these 2 words already occurred in the sequence. So that's how the RNNs basically work. So we have visited this idea, I think, in the first session. We looked at LSTMs, which is a very, very special type of RNN. So we'll just look at why exactly was this LSTMs and other GRU, which is GRU or LSTMs, are required. So if you have trained these deep neural networks, or if you have looked at the blog post videos, of all those people like Andrew Ng or Siraj Raval, you might have heard this term very much, vanishing gradient. We have looked at the vanishing gradient in a previous session. Let's just recap. So the vanishing gradient comes from it's coming from a mathematical background. I don't know where I write the equation, but let's just forget about the equation for now. Let's just focus on the intuition. So vanishing gradient comes from, so let's say this is a pretty simple sentence. This is a forward. So let's say I have a sentence of, let's say, 20 words, or let's say 30 words. What happens is, you remember that A1 actually includes the idea about I, and A2 will actually include the idea about I am. But as you move on through the sequence, what happens is the hidden state will actually start to include the idea about I am. They will forget about the first words that appear in the sequence. So if you have a really large sentence, let's say the common example that Andrew Ng uses will be the cat ate pizza, he ate cake, he ate a cake, he ate milk, and a lot of list of such applications, and the cat was full. This is going to be a long sentence. You can add all kinds of food the cat ate in between, so you get a pretty long list. So you get a pretty long sentence here, about 20 to 30 words. So what happens is, you start up with the cat, and you are ending with was full. So the cat ate this and this and this and this and was full. So when it says the cat, you said the cats. So if you say the cats, then you have to actually, instead of was full, you have to use were full. So you have to keep that subject agreement. So our subject was singular in the first case, it was cat. So you will use was. But when the subject is plural, in our case, if it's cats, then we have to use were instead of was. So in the pretty long sentence that we have, the problem with the basic RNN or any other kind of deep neural networks would be that the idea about those first words, the cat was one of the first words in the entire sequence. So the model would almost forget about whether it was cat or cats towards the end. So this is caused by a lot of mathematical consequences of how the model is trained. If you know about backpropagation, you can get some kind of intuition, because you'll be calculating the gradients and you'll be passing it backwards through the entire model. So what happens is the layers closer to the output layers might be faster to learn, and the gradients will vanish or come closer to zero as we move forward. That's the intuition. If you know how a deep neural network is trained, then you can get that intuition. But either way, you should just understand that the first things that appear in the sequence might be forgotten by the end of the sequence. So this is caused by this vanishing gradient and similar memory compression problems, which are more technical in details. So this is why we created the idea of GRUs and LSTMs here. So LSTM stands for long short-term memory. That's the one we discussed in the first session. And GRU are gated recurrent units. So in the case of LSTM, what you are going to do is you're going to create a memory cell within your basic RNN unit. So what it does is, when I saw the word the cat, then the LSTM will suddenly try to memorize that the subject was a singular subject. So it was cat. So throughout traversing throughout the sequence, the memory would still hold that the subject was a singular, until the final point where it has to be used. So you get to the final point where you have to make the decision between whose or where, then you can simply look into the memory whether the subject was plural or singular. So that's how LSTM would work. Also, GRU is gated recurrent unit is also a kind of recurrent neural network units that we use. So it also has some mechanism by which you can memorize things using some form of gates. So those are LSTMs and GRUs. So even though you might see LSTMs much more than GRUs in the literature and in application, GR is actually a more latest model out there than LSTM. LSTM is probably, I think it's older than us. It's about 1997 paper LSTM was discussing. So LSTM is pretty old, but it works pretty well. So GRU came something like for a more generalized structure to LSTM and maybe a bit more easier to train LSTMs and all. It's pretty new, but still we use LSTMs. So these are the three. This could be considered. We could call this a vanilla RNN, I guess. So this is the basic one we saw. We get the input here. This kind of structure we might see in some literature, but this unfolded structure is what usually people would prefer when we represent an RNN. So this is the structure we first drew as well. So here we are actually taking W instead of that A we used, and the input goes in, the output comes, the new hidden state is produced, new input comes with this hidden state, and the input you get the new output and the new hidden state. That's pretty much, we understand that. LSTMs are also similar to this, but instead of this circular boxes here, we would use this particular unit. So you should, it's okay if you don't understand all these arrows. You might have two more arrows here, I guess. In the usual RNN, you can say there's one hidden state here. In the LSTM, you might have two hidden state here. There are two arrows that goes out, and there's an output arrow. It's optional. Also, you don't have to care about all these equations, but equations are easier to make a sense of what the LSTMs are. With more rigorous mathematical background, you can actually look at these things. You might understand a few of the things. I think the screen is not clear enough for you to see the details in it, but you can see that these gates and the input values and the kind of sigmoid function, tannist functions and the gates that goes here. You can see all those details in the Kola GitHub Understanding LSTM's blog post that Joel shared in the group. Also, a bit different to us could be the GRU, or the gate and recurrent unit, which came much after the LSTMs, but they didn't really go places. So GRU is much easier to train, and it's more general than LSTM. So it kind of, LSTM would perform better than GRU. So this is the de facto standard, I guess, if we use say RNN. So like this, we talk about encoder decoder shortly, but let's just say, when you see these units like RNN units written somewhere in blog posts or videos or any other literature you see, you must understand these RNNs can be any of the three we discussed here. It could be just some vanilla RNN, which might simply use some linear function inside this, or you can use all these gates to compute two hidden states, or you can use GRU to compute one hidden state, or whatever. So these boxes could be anything of that three. So this encoder decoder structure is one of the most important structures that ever came to NLP, natural language processing. So why is this important is, you might remember from a few slides before that we talked about this many-to-many structures. There are two kinds of many-to-many structures. In the first one, you actually have the same dimension for the input and output. But in the second case, you have the different dimensions for the input and output. So these kind of problems are very, very common in our applications. Let's just say, just for the example, our main focus is going to be on machine translation, particularly neural machine translation. Machine translation, exactly one of these problems. So let's just say I am a man. So in Spanish, it would translate to yo soy un hombre. So that'll become forward. Okay, it was forward in English. Sorry. So the main difference is sometimes in the French, for example, the French is the common standard. We use French or German is the common standard to be used in. So in this paper, we are actually discussing. This is the paper that actually first, for the first time, this is the paper that discussed the use of in machine translation. We haven't yet talked about attention, but we will look into it. This is the paper that first discussed the application of attention to neural machine translation. So these guys are using English-German translation. So the thing is that when you translate, you might see that there's a mismatch in the dimensions of the input and output. So that's why we use the encoder-decoder models of the RNNs. So essentially, what we do is we take an input. Let's say I am a man is a sentence, or I am man is a sentence. So you give I here, you give am here, and you give man here. So sorry. So instead of immediately outputting whenever you see an input, you will just hold out on this output for later. So whenever you see this input here, let's just say I am student is what I want to encode. Then I will just input it into the network, and the network is essentially going to make a representation of this sentence. So when I say I am student, it is going to take it as input, and it is going to crunch it into all the numbers and will create a beautiful, maybe sometimes ugly representation of a large matrix, which will actually point to this sentence. So maybe I take, let's say, a different example. Instead of I am man, let's say India is an awesome country. So I create this sentence. I also give this to the encoder, or this RNN unit here. This part of the entire model is called the encoder, because we are giving this input and we are creating a representation of this input, which is what we call the encoding. So this is the encoder part. So I give the input, India is an awesome country. So this is also going to create, let's say, a large matrix. In this large matrix, there are going to be numbers ranging from maybe -1 to 1, or maybe 0 to 1, based on the kind of embedding you're going to use or the structures you would like to use. So this part would create such a representation, and the final output is going to be an encoded vector which would represent this entire sentence. So you might see this part. This part is going to be the decoder. What the decoder is going to use, it's not going to take the inputs like the sentence. I'm not going to give the India is an awesome country in the decoder part. Instead, I created the representation, and I'm going to pass the representation to the decoder part. So the decoder is trained to decipher that large, ugly matrix that we created to represent our beautiful statement. So I create India is an awesome country, and that's going to be an ugly matrix here. And this RNN is going to take this ugly matrix and is going to spit out as output, again, a beautiful sentence in, let's say, Spanish. So it's going to be, I guess, India es un país bonito, I guess, something like that. So that's going to create the output here. So that's the encoder decoder structure, and this encoder decoder structure is the most important structure that you might see in the papers. So if you look at this paper, there are a few, I think there are some citations here. So this is a paper in 2016. This is by the Jacobs University Bremen and the University of Montreal. This is the first paper to apply attention to neural machine translation. We haven't yet talked about it, but this paper also shows us some bit of the encoder decoder structure. So this is going to be an encoder structure, and this is going to be a decoder structure. We're going to talk about what there's in the middle later. So you should be pretty familiar with. If you look at all the papers that's been coming in NLP for the last, let's say, 5 or 6 years, you might see encoder decoder used a lot. So that's about encoder and decoder. So I guess you understand that. So you must understand, by now you must understand that LSTMs are good, encoder decoder structures are good. So instead of using the vanilla RNNs in here, you're going to use the LSTMs, which already have some memory into this RNN. So why did you do this? You have to, you do this because you have to handle larger sentences of, let's say, 7 to 10 words, I guess. So that's a pretty large sentence, pretty small compared to what we are going to talk about. So you squash LSTM into this encoder decoder structure, you expect to get a good result in it, and you actually get a good result in it until this is the kind of sentence you're dealing with. So you might remember this guy, Louis, from the Ant-Man. So he always has this way of storytelling. So you might say this is one really large sentence. So it goes like, well, my cousin's ex-wife's personal trainer, Scansor's Lorna states his second favorite messages has assured me that there's some old guy named Michael Douglas living in this. So you must understand. This is a really, really large sentence. And you must see all the kinds of dependencies that goes here. My cousin's, ex-wife's, personal trainers. So you understand. The LSTMs are good until the kind of sentences is not like this. Or let's say Louis is not using the LSTM. Then it's good. But if he starts using it, it's pretty problematic. Because our sentences are really large for the LSTMs. So LSTMs are like, how could I do this? So that's how it goes for the LSTM if you see large sentence. So with that, we will come to some limitations of the LSTM. LSTMs are good, encoder decoder networks are good. So putting LSTMs inside the encoder decoders are really good, but they're not good enough. Let's get some limitations. So these limitations I got from I think the attention paper. Okay, I think this paper discusses some of these problems. Also, there are some really important papers. These are some really important papers. Shaw et al. 2014 and Suskever et al. 2014. I have the links in the presentation, and I will share the presentation later. So you should look at this presentation. You should look at these papers to actually get the idea about all the limitations that LSTMs might have. So the first one is obvious. Whenever we create one network, let's say I create a network and I train it and we're happy with it, other guy uses it and he's going to say, well, it's very difficult to train it. So the LSTM has such a limitation, so it's very difficult to train it. The one thing is it has very, very long gradient paths. Now, what does a gradient path mean? So we have, okay. So
Hey, Nitin, are you speaking? Not able to hear.
Hello?
Yeah, yeah, now we
Okay,
can
okay.
hear you. I think we
Okay.
just went away for like 10 seconds or so.
Okay, okay. I think the net is over. It's fine. So we were talking about the gradient paths. So can you handle the sentences like the one that Lewis might give? So you don't know really what this he is going to represent. All these cousin or ex-wife or personal trainer, cat owner, Senator Michael Douglas. Who is he going to talk about? So when you represent that such a sentence in the LSTM, what happens is when you the senator, let's say the personal trainer appears somewhere like here, and the he is going to come somewhere like here. So when you have to check who the he is, you're going to travel like from here to here to here between all the units that were here. So what happens is, remember about the gradients we talked about and the backpropagation algorithm. We didn't really talk about the backpropagation algorithm, but if you have the intuition, it will be fine. So when we do that, we pass these gradients throughout backwards through this network. And what happens is, the first words that came here might be a poor representation at this state. So this he cannot be all these words. So in this case, this is Michael Douglas actually, but it's even this Michael Douglas is somewhere like 10 or 11 words behind the he. So we have some real problems here. So that's it's not exactly the vanishing gradient kind of problem, but it's a different kind of problem. Let's just say LSTMs are not really good with this long gradient paths. The gradient paths will get so long in a very long sentence, and this will mess up a lot of things. And the really important thing is transfer learning. So transfer learning is one of the important kind of technologies that we use in the entire machine learning field. So the idea is we train a large network with a large data set. So some really big players like maybe Google or Facebook or OpenAI will train this large system on really enormous computers, and we get a baseline model. And we take this baseline model and we with our minimal systems, which have, let's say, limited RAM and limited computation and GPU systems. We might just have to fine tune this baseline model. So you don't have to use this entire billions of lines of data to train your model. You take this billions of line trained model and you fine tune it on what you want. Let's say you have this BERT, the ART BERT is one of the famous language models. So you take this BERT and you, let's say you want to apply it to medical field. So there are lots of pretty jargon in the medical field. So you have to create a data set of these medical terms. And instead of training the entire model on all the ideas about the language, you don't want to teach it about the you don't want to teach the model about the grammar, you don't want to teach it about the sentence structures and the meaning of the structures. You only have to deal with specific things that your field requires. Let's say a medical term, you need to handle about just a few words. Few words that are important to the medical field. So that's what transfer learning is, and it is very important for a model to be capable of transfer learning. So what LSTMs does is they're not good with transfer learning. So there has been a lot of attempts on for using transfer learning on LSTMs, but a lot of state-of-art models later came out which doesn't use LSTM. So transfer learning is not good enough in LSTM. So just because the transfer learning is not good enough, you must understand that also the every different task with a very specific level data set is required for every different task. So if so you might be familiar with CNN, where some image recognition models where you can train your model on cats, then you can do some fine tuning and ask it to detect dogs too. So you do have some label data set, but still, in the case of LSTMs, people need very specific label data sets, which has to be pretty large enough to actually make it good enough. This fourth point is somewhat of a consequence of the third point, which is also a consequence of this point. I think all the points are a consequence of this point, but it doesn't really matter. These are the limitations of LSTMs. So this is why we needed something more. We needed something more to handle the difficulty in training. We needed to avoid these long gradient paths. We needed to do this transfer learning and all these things. So that's why we came up with introduced the attention mechanism. So attention mechanism, as I have told a couple of times already, was first presented in this paper, Neural Machine Translation by Jointly Learning to Align and Translate. This is 2016 paper. I think it's a 2015 paper. It's published in 2016, I guess. So if you ever read this paper, you must understand that it talks a lot about the neural machine translation and statistical machine translation. Then it's going to talk about all the improvements that happened in the machine translation. These links are there in the presentation I'll share. Also, it talks about the previous methods that we use, like the phrase-based translation that we first talked about, in which you have to fine-tune on everything hand by hand, which was a tedious task. Also, you will get the idea about the encoder-decoder networks here. You will have some idea about it. This is the paper, so et al. 2014 A and B was the papers that discuss the encoder-decoder models for neural machine translation. So that's pretty much a lot of background details are explained in this paper. Here you will have the, okay, this image I will have. Okay. So this is the basic encoder-decoder model. To be honest, this is a simple encoder-decoder model, but there's a slight differences here. This is the encoder part. You might see there are two boxes instead of the one box we used to see here. There's this one box here, and there was just a one side arrow here. But in this case, we have two boxes inside every unit, and there are arrows always forward and backward as well. So these kind of RNN structures are called bidirectional RNNs. That's obvious name because it have forward arrows and backward arrows. So the basic idea is, instead of reading from the first to the last, they also read from last to the first. So in this case, okay, let's say we take some sentence. Let's say this is the sentence we take, learning to align and translate to the sentence we take. So the forward propagation will read as learning to align and translate, and the backward propagation will at the same time read from translate and align to learning. So this is a way of actually getting the dependencies from the future. So let's say I write a sentence. Okay, I'll write this here. I don't know what it is. Let's just say I am writing something here. So so I'm going to write Teddy Roosevelt was a good guy. Okay, this is one sentence, and I'm also going to write another sentence here. Teddy bear is wonderful. So I have these two sentences here. So if you remember from this forward propagation, when you read Teddy, you don't really know whether it is Teddy like the President Teddy Roosevelt, or is it the teddy bear? So you don't really know. So you haven't seen this word yet in the forward propagation. It is the next word. So you don't really know what Teddy means. So this is not actually a good example, but this works. So when you train an RNN to also look backward, what you get is when you read Teddy, you know, okay, this is the Teddy Roosevelt. And when you read this Teddy, you know, yeah, it's a bear. So that's the kind of difference when you get when you do the bidirectional RNN instead of the unidirectional one we see before. So that's the kind of RNN. The bidirectional RNN is the one we use in Baranyi paper. That's the Baranyi paper. Our main paper is the attention model, and it is the Wastrani et al. Paper. This paper is the Baranyi paper. Okay. The Baranyi paper model has a bidirectional RNN encoder and a usual decoder here. So in this structure, the previous encoder decoder structure we've seen, you remember that I used the sentence "I am student" and I created an ugly matrix here, and also I told about what was it? India is an awesome country, and I created another ugly matrix for it. So whatever input you actually give here, let's say 3-word input, or let's say 10-word input, or a 30-word input, you finally get one ugly matrix. This matrix could be of a fixed dimension, let's say 100 to 300 dimensional vector it is. So whatever input length you give as input, you still get a fixed length output. So that's the kind of encoder we have here. And the decoder is going to use this same vector for every input. So this is a 300 dimensional vector. This first unit will use it, and the second unit will use it, and the third unit will use it. And all the units will use the same context vector. That's the word we use here. It is a context vector instead of the encoded vector. So this context vector is a fixed length, and that's what we use throughout the decoder. And there are certain bottlenecks when you try to represent everything with the same length vector. So you, it's obvious to understand it. So if it's a 3-word sentence, a 300 vector, a 300 dimensional vector, maybe a pretty waste of memory. And maybe if the sentence is like a 30 or 50-word sentence, then the 300 dimensional is not doing good enough. So that kind of disparities happen. So that's why the Baranyi paper actually introduced the attention mechanism. So in the case of attention mechanism, what we do is, instead of this common context value we use, we are going to use different contexts for every unit in the decoder. So when I take this unit, I'm going to compute one context for this value. If I'm taking this unit, I might compute a different context vector for this unit. So for each unit, we will create a different context vector here. So you can see here this. Here is where we create this context vector. So from the encoder output, you're going to create this weights. These are alpha T1, alpha T2, alpha T3. We are creating this weights. So let's say I am translating from English to Spanish. So I am at the teeth sentence. Let's say teeth word. Let's say I am at the third word in the output translation sentence. So T is going to be 3. So what I'm going to do in this context vector calculation is, I'm going to look at how important each word in the input sentence is to this particular word. You might use this example here. So the left side, this is a French translation actually. It's French to English translation. This is the one example that's from the Learning paper 2015 that I just showed you. So this is the input and this is the output. So you must understand that this is the de facto standard of attention picture that you will see throughout the web. So you can see when translating lay, you can see that this lay to the, you can see that okay, the translation is other way around. So this is our output vector and this is our input vector. So this is going to be our T1, this is going to be T2, T3, T4, T5, T6, and so on. So when you first take the T1 output, you're going to look at, you're going to create a context. By context, I mean, what are the important terms in the input vector that you have to actually care about? In this case, you're going to create you're going to just look at this. You can see that all these values in the input is blackened out. Blackened out means this term really does not care about all these words. It's going to directly translate lay to the. That is, it doesn't really care about anything else, and that's exactly what we have modeled with the attention. So the mathematical details about the attention, it's not pretty complex. If you have a basic idea about the deep neural networks, or let's say you have some idea about neural networks in general, then you can read out the paper and get the idea about all these equations. These are the, you're actually creating a conditional probability. You don't have to care about that. So you'll get the idea about, here you'll get the idea about the kind of attention we'll use. We talk about this specific equation later, so don't worry about it. So when you see at the, let's say you are taking T2. When you take T2, it's a word agreement, so it's going to again scan through the entire input to see which words should I really attend to. When reading this, when trying to generate this term agreement, the model will understand that it has to only look at this word accord and it doesn't really care about all the other words. So that's how we go on, the agreement on, and here onwards, there is something really interesting going on. So here you're going to actually translate La Zone Économique Européenne to the European Economic Area. So if you see in the French translation, there is Zone Économique Européenne. And in the upper translation, you can see that the order in which it comes is actually reversed. Zone translates to area, economic translates to economic, and European transport to European. So the order is reversed in the upper translation. So this is achieved, and this is a consequence of the attention model, and this is one of the greatest achievements of the attention model. So when you read or you are trying to generate this, let's say T1, T2, T3, T4, T5, when you're trying to generate T5, you're going to look at what words should I really care about. And the model is going to tell you you're going to care about European and economic A. You can see that European really gets a higher value of attention and economic A gets a smaller value of attention, and other words doesn't really matter. So this is the core of how attention works. You can also see, as I say, this is T6, economic is T6. So when you're trying to generate economic, the word economic in English, you're going to ask the model, what words in the input French sentence should I care about when I create this word? So the model says that you have to really care about the word economique and so on. So you give most importance to this word, and you give some more importance to this word and don't really care about the others. So this is the core of what attention means. And you can also see was signed is changed into ethesine. I don't know if that's how it's pronounced, but let's see. So was signed also has this kind of attention here. So these are the attention matrices that we will see in some typical attention models. And this is the core idea of attention. You care about only the things that you want. You just ignore everything else. So in this context vector that we previously had, in this context vector, you have a representation for every input. So each unit is actually looking at every other input. So this is clearly waste of computation, and this is clearly waste of our time as well. So that's why we are going to, whenever we compute this, we are going to create a context vector in which we will understand which was in the input I'm going to care about. And I'm going to leave out everything else. I'm just going to attend to things I need. This is more or less like how human attention works. That's this is a mathematical formulation for the human attention, let's say. Now, does attention really work? Well, the research says so. If you look at this, the sentence length is from here. It is from 0 to 60 sentence lengths. These downward graphs, if you look at them, you can see that they're actually the usual LSTM ones. We use the encoder-decoder architectures with the LSTM. They do somewhat as good as the attention up to about, let's say, 20 words. And above that, they're going to really flop down, and the attention is going to just stay like, I don't really care about the sentence length. So I don't really care about if it's Louis, or I don't really care about if it's anyone else. So, but here it is, the LSTM and encoder-decoder models say, oh, it's Louis, I can really work again.
Okay, I think there is some issue at Nitin's end. He has left the call apparently. So I think we just wait for a moment. Oh, he's back. Okay. Hey, Nitin, everything's all right?
You connected?
Yeah, I can hear you. Something happened?
Yeah,
Okay, okay. It's going good, by the way. I checked with others. Sriyar is kind of getting it, no props. And yeah, it's going good, man.
Okay. So let me just try to connect the system. So we already talked about something like attention. We started from the sequence. What are sequential data? Then we looked at how we will model the sequential data, what kind of sequence model makes sense. And we talked about RNN. If you don't really understand all the details, it doesn't really matter. RNN was just used for sequential modeling. And we looked at how encoder was good at handling translation problem. We used LSTMs in encoder-decoder models. Then we understood that using a fixed length vector is always some kind of bottleneck in our system. So that's why we created the attention mechanism. We created the attention mechanism so that we can just focus on whatever we really care about. So, by the way, this, if you look at most of the sequential kind of problems that are in the industry right now. So let's say it's audio generation or image classification has been tried with these transformers. That's really well. But a lot of such things you can look at something like Papers. Papers with Code is a famous site. You might know the Papers with Code site. If you go go to there, and you will be able to see all kinds of models and structures that use this. There's just one more point that we have to really look into before we understand transformers. So you understand one more specific point, is the self-attention. You're magically going to understand transformers. That's just one more topic that's going to be in this. Have you seen this GPT-3 and all such things are coming in the news and all such things? So this is coming because we have got really close to actually modeling languages like the way humans do. So GPT-3 is really good. GPT-3 is really good in the way you might have seen this one application where you actually just say that I want a website which has a button, and when I click the button, I will have to add something to the cart. I just say this to the GPT-3 model, and it's going to be able to, with some other instructions, obviously, it's going to help you create the entire website assets. So I say, I want this button to do so, and the system will magically do it. That's the kind of application that these language models that use this attention at their core happens. So coming to more about the this attention mechanism, we have seen the name of this paper that we have seen. So this paper discusses about attention is all you need. So we saw that attention is used along with the encoder and decoder structures. So we saw that the encoder is going to create some representation of this sentence, and whenever you're going to decode, we are going to actually create a context vector for each unit. So basically, the attention is working along with the attention is working.
Nitin, actually,
Okay.
we can't see your slide now. I feel some setting went wrong.
Yeah. Just, okay. Let's see. Okay, while I'm setting, I must just continue with the talk. Just hear it. I will talk about with the slides shortly. So the idea we talked about was we are using attention along with the encoder decoder models in what we were talking about. So this is something that really was not feeling good for the people at Google. So they said,
Nitin, we
yes.
still can't see the presentation.
Yeah. Can you see now?
Yeah, the new user on one is seen, but the screen is yet to load, I think. Oh, it just left now. Now only five of us
Okay,
here.
I'm trying to. It's coming back.
Yeah, it's back.
Okay. The system went away, current went away. It's raining and all that stuff. So We were talking about the attention will be introduced. Now we can see the screen, right?
Yeah, we can see the screen. It's good. It's good.
Okay. So we were talking about the attention introduction. We told that these are the structures, these are the graphs for the encoder decoder structures that use attention, and these are the other ones that doesn't use attention. So we talked about this. Really long sentences not really matter for the attention system. By the way, this score is the blue score, BLEU. I don't really remember the full form. It was I don't remember. So the blue score is the standard metric that we use in language modeling and translation mainly. So the idea is, you might know in the usual neural networks, we have one correct answer. So you can just compare the correct answer with the answer you created. So that will give you the idea. But in the translations task, you know that there is no one correct answer. You might have a lot that are good enough. So blue score is something that looks at how good one translation is. So something like a 20, this could be something like 28, and 28 is something like a good blue score when in 2015. This has grown really something to 35, 36 maybe now, or maybe higher than that in some models. I don't really remember. So this is the impact of attention. This specific paper that we discussed, the Badanu 2015, where the attention mechanism was first discussed. This paper is one of the most cited papers in the natural language processing, I think. It has more than about 3,000, 6,000, I don't know, something between that number of citations. So our main paper, the attention is all you need, also cites this paper. So this is where it all started. We can know that when attending to certain things that we only need, the system can perform really well. We can train really better. We can train faster. We can use a lower number of data. We can get better inferences. We can get better blue scores, which means higher accuracy, and we can handle larger sentence lengths. So they introduced one kind of attention, and then right after that, a lot of people got really interested or really attended to the mechanism of attention and started developing different mechanisms you can do for attention. So the kind of attention that the Badanian used was called additive attention. This, by the way, is a graph I get from papers with Quartzsite. If you go to papers with Quartzsite, there is a section called methods. I can show you later. So this method where you can actually see different kinds of mechanisms that you can use. You can use, let's say there is a is for polarization, there's one for normalization. So additive attention is the one that this paper actually discusses about. And you can see that additive attention was pretty much rarely used. The main paper, the first time it was used was here in this paper, and it was rarely used, and a few people used here it in 2019-20 gap. But in 2017, something happened. Something new came here. Scale dot product attention, and this simply took off. You can see the graph. It took off like too much, and you can see where it is now. Now, this graph is, you can say, the number of papers that are using this specific technique. So you can see something happened in 2017 that really took off. Additive attention came first, but something else happened. So you can look at the kind of attention. So in the attention, you might remember that we are going to compare, we are going to create a context vector that will tell us which part of the sentence is important. Now, based on how we decide something is important is how we decide which of these attention mechanisms we use. So this site, Lilian Wang GitHub page, This one has a really good blog on attention. This is a lot of things about attention. This is the attention that they use in image recognition. So you just cut away this part, and I just show you the picture, and you can still say there is an ear of a dog here. So you know how things work. So that's the basic idea of attention, and this discussed really well. The encoder decoder is discussed. This is the one we talked about in the Betanu paper. And there's a lot of mathematical details here. So we will talk a little bit about the mathematical details here. So we have seen this diagram. We've seen that the European Economic Area is actually reversed of Zone Economic Area European. So this is based on a score function. So by the score function, what I mean is if I give this position input and I give this position as another input to a function, I should be able to know how much these two are related. So obviously this word is going to be very well related to this because they are actually the same word translations. So you're going to take this term and you're going to compare and you're going to give this position into a function. Okay, and you're going to give this position to a function and you're going to iterate over every other inputs in the input. So this is how you calculate a score. In this, you can see this is a tan function and applied to some other linear function. Essentially, this is a feed-forward neural network. So what you do is you give this position and the other position into a neural network like the one we used to know, the feed-forward neural networks like we know. So this function is a fancy representation of that neural network. So that's how we know that's how we know these attention values here in the paper. What has happened in 2030? That's what we are going to look at. So if you look at this, there are different family of attention mechanisms. The one we talked about is this. This is a feed-forward neural network. And then in 2015 itself, there came another score function, which actually, let's say, HI is the target, I mean the input value, and T is for the target. So when I'm going to look at this example. So when I look at this, function, when I look at this attention scores, I may say this word is related to this word, and the score is the HI is going to be essentially a representation of this, and ST is going to be a representation of the output. So you might get the idea, the output and the input part. So after this one, we talked about the dot product score came into existence, and this was really influential also. This is a Luong 2015 paper, and the Luong 2015 was also another influential paper that discusses a lot about attention mechanisms. And the score is just calculated as a dot product of this representation of the output and the representation of the input. So that's pretty much it, just the dot product, and that's all. Well, if you have some idea about the NLP, you might know, why not just take the cosine similarity between two vectors? So I have a representation of the input, and I have the representation of the output and the representation of the input. So just take the cosine similarity and you can get a score. This is a content-based attention, which actually came before this additive attention that we talked about, but it was not explored further. Then came the dot product attention. We just take the dot product, and that's a way we handle it. But what happened in 2017 was our paper came about. Our paper was the Vesvani et al., which is the attention is all you need paper. So they're going to tell you that you don't really need an LSTM, you don't really need an RNN, you don't really need the encoder decoder structure that you created. You can simply use attention. You simply use attention and you can create a really well translation. So that's what these guys told you. So how they are going to implement this attention is using something called a scale dot product. So you might know dot product of the matrices here, and when you take the dot product, you're going to get one scalar value. Let's say you get a value of, let's say 16 is the value you get as this score. Okay. Now, what you're going to do is you're going to divide it by the number of dimensions that you use. Now, this is something like a normalization. You could say it's some kind of a normalization. So you get this scale dot product. So this is there to avoid this dot product exploding. So let's say this dot product gets into 1,000, then it gets to 2,000, it gets to really, really large values. So when you divide, you can always keep it in some specific range that your model is really comfortable in. So that's a scale dot product attention. Now, this came into existence, and it really started to become the de facto standard in attention mechanisms. So you can see the scale product came here. Then in 2018, it was still explored. Then actually came the BERT and all other representations or language models, and the GPT and all came. Then it really took off. Then it took off like too much. So that's the kind of attention mechanisms that we use. Also, there are different kinds of attention modules that we use. If I keep telling you like this is going to be really boring. It's already getting boring. Let's just start to focus on the paper itself. So if you try to read this paper I actually found it a bit more harder to read than the original attention paper, because I think it kind of needs a little bit of background knowledge before you actually read this. So they assume it's a research paper, so they might assume that you know about all these things. You know about the state-of-art process, you know about the recurrent neural networks and all such things. So I'm just going to focus on the most important contributions of this paper. And let me introduce you the transformer. This is the key thing, the most important one of the models that we use these days. This beautiful thing here is what we call the transformers. So you might remember that I showed you a transformer pic. They don't really use this picture, but by the way, I used it. I like it. So this transformer, you might see that this actually has an encoder and a decoder, but they don't really use any RNNs inside this. They don't really use LSTMs or GRUs inside this. So you can see they simply just throw away the word attention here and there. There's one here, there's one here, there's one here. Just throw over the word attention, and they just escape with the attention itself. So that's why they tell you that attention is the only thing that you really need. So let's just focus on how this attention works. Let's first focus on the encoder. So if you don't really understand about all the details of the transformer, it's fine. You just have to understand that transformers are the de facto standard of language modeling and any other sequence model right now these days. So you go to sites like Papers with Code, or you go to Connected Papers or Semantic Scholar. You'll see that this model is kept using. You are keeping using it in almost every aspect. So obviously, this is a Google paper, and also Google is still maintaining this. They have a package called Tensor to Tensor, which is a TensorFlow implementation of this transformer. So if you don't really need to understand these details of this transformer, all you have to understand is this. This is a standard model, and this works on the idea of attention, and very specifically, it works on the idea of self-attention. So I think I have a slide for self-attention. So when you talk about self-attention, this is something, this kind of image you kind of get. Self-attention, you kind of look into the mirror yourself. So what self-attention necessarily is, instead of looking at, when we talked about attention before, I took a word from the output sequence and I looked into the input sequence to check whether what I had to attend to. But in the case of self-attention, what we are going to do is I take one word in the input sequence, and for this one word in the input sequence, I'm going to scan through the input sequence again to know what words in the input sequence I'm going to attend. So, for example, let's go back to Louis here. Louis is really helpful today. Okay, so when I'm reading this, so I get this. Let's say this personal trainer is the word I am looking at right now. So when I'm looking at the word personal trainer, this is the input sequence. I'm going to take the word personal trainer in the input sequence. Then I'm going to look throughout this input sequence, and I'm going to make a sense of which words really are bothering this personal trainer. So if you attend to this part, personal trainer, it is ex-wife's personal trainer. Who's ex-wife? Cousin's ex-wife. Who's cousin? My cousin. So this is the part you will attend to, and also you will attend to this part, the cat's original owner. So trainers, cat's original owner. So you know that the personal trainer, whose personal trainer is this, and what does the personal trainer have? This part of the input sequence, your model or encoder is going to attend to. This is the idea of self-attention. You attend to your sequence itself. You're going to look at what part of the sequence you really need to encode this sentence. So previously we used to give a comparison. Previously we used when you use attention, when you had to create the output sequence, you looked at the input sequence. In this case, we are using the input sequence itself. That's what self-attention really is. And that is at the core of the attention is all you need paper. So this left part, so we're going to be through of the details of the transformer. So the basic idea is it is the standard one, and it has the self-attention. It is main topic, and it's based only on attention. It doesn't use RNN, LSTMs, or anything. And a few more points with which you can just wrap up the transformers. Then I'll go into details if you need. So the basic idea is transformers have performed really better, much better than any other models that ever came into. Now, this is partially due to the computational advantage this specific architecture will give you. So the idea is that instead of the sequential structure that we used to handle, so when I told you the sentence, remember the sentence, I sequence. You took first icon parallel. So that's one important bottleneck of these models. So that's where transformers came, and they told you when you use just attention, you don't use RNN, you don't use LSTM, you just use attention. When you use attention, you can just make everything parallel. You don't have to pass each word separately. You can just pass them all together. You can just pass them all together, and the network will learn everything together, and it can be massively parallel. That's the one advantage that transformers came, and this is the one reason that the models like BERT and GPT came to existence, because the transformers are really good at keeping the training and the computation and the storage that we use at check. So we can use massively parallel architectures like TPU, which is Tensor Processing Unit, or the Graphic Processing Unit, GPUs, to make this parallel learning. So that's the idea about transformers. I don't know. Do we have time, Joel? Should we go into the details of the encoder and decoder?
Yeah, I think this is good. Unless Upsal and Srihari have a different opinion, but I think it's good, man. Like you did cover a lot.
I think the details are a bit more. Let's say we have there is a layer normalization, there's a feed-forward network, the multi-head attention. So there's a lot of details we have to go into. I don't think the time will able to cover it. So we already have the basic intuition of the self-attention. So I think we are good. I'll just give you a few more pointers from which you can get into the transformers more. I think that should be fine.
Okay, sounds good, Nitin. Yeah. So, can I add on to this like a few
Yeah,
points?
sure.
So like okay, so like Transformers is all around, like, when it comes to like uh NLP, that is like pretty much the standard right now, because like, yeah, because like most, even if you're doing most challenges, they say like, like attention based this thing is required, because that is what most people are using. It's kind of the approach most people are going through, but like depends on use case. The thing I really want to add was like, this transformers are also like making in like attention and transform mechanism are also making into other fields. Like I came across a paper where like, traditionally you use something called GAN to like increase like picture quality and things like that, to picture recreation and things like that. So now they are actually using image transformers, like attention on images, to actually like do those kind of things right now, because image transformers are actually becoming a thing, and like transformers are also common in like audio and things like that. So it's like, it's not just NLP, it's kind of dominating most kinds of research right now.
Oh, that's interesting. I didn't know about image. Like, I mean, what's the use in image case? Like, you can do like how Dreamy effect came, right? Some neural network
No,
was
no,
that
no,
made.
no. Like, if you're like trying to increase like what is the quality of an image, or like even for something, this thing is image captioning. So now we have attention. You can like determine which are like parts of images are like, important, so as to like form an apt description of an image. That is one use case. And other is like for you to able to recreate pixels. So like traditionally we use like GANs for like, increasing quality of an image, or removing watermark, or like doing things like that. But now I think like I came across a paper written like recently where like it was using concept of image transformers to actually recreate images, like predict pixels and things like that. So now we have like, okay, this is a cat, so now like you can recreate images of a cat and things like that.
Okay, cool. So we're just identifying portions of an image, isn't it?
Yeah.
Yeah, so adding to that, you can actually look at the Papers with Code site, and you just go into the browse the state of art models, and pretty much like Hari has said right now, you take any class and you just go into their leaderboard. You can actually see that they will use some form of and attention mechanisms in most of these structures. So this is what a speech recognition structure. So in this net, the ResNet is used and the bi-LSTMs are used. This pretty much uses an attention mechanism. Also a few others. Also in other. Okay. This is the visual navigation one. I think the paper that Hari told was about visual navigation one. I think I have read that recently. That's what I was searching for. So the visual navigation, I think they are using this transformer kind of technique to attend to specific parts for the navigation. So also one more thing, this the jukebox is a generative model like the GAN model, which I just told about. So this jukebox also uses the transformers. They use also autoregressive transformers to at the core of this structure. So transformers are pretty much touched in every part of this fields we can think about.
Yeah, Nitin. Actually, I just now was browsing on the website. I came across a very similar title, Hopfield Network is All You Need.
Yeah.
And that came out like 2 months ago or something like that.
Yeah, like once you have a catchy name, you just stick with it.
Yeah, they mentioned, I think it's like the next thing after attention. But yeah, anyway, that's for next time, I guess. For
Yeah.
now, let's figure out attention.
Yeah. So
For
anybody has?
transformers, there are certain limitations to transformers as well. Like you really need some big players like Google or Facebook or Amazon, someone like that to actually really train on really large networks. So that's still a bottleneck in this aspect. So we're still looking at the ways we can optimize transformers. So just go into artsci.org, you can still see a lot of new research papers coming about talking about the limitations of transformers and using different representations and all.
Yeah.
So that's also
Speaking of
an
which,
open field of work here.
like connected papers is a good resource. Like if you have a paper and you're
Yeah.
like searching for related papers, like connected papers is pretty good. Like they'll literally build a graph for you, like on dependency on like all technologies that use this paper.
Yeah, Nitin had mentioned it, right? You mentioned three links. One was papers with code, connected papers, and forgot the last one.
Semantic Scholar. Next. Can you see the screen?
Yeah.
Yeah, yeah.
Yeah, this is the Semantic Scholar. So you can see
Okay,
the number of
semantics.
citations the paper has and other papers on which there's a high influence of this paper. So basically, when you're reading a paper, you can actually get the papers that are sourced to this paper, but you can then you just go to the references and you can see all kinds of paper that were used to create this paper. But the main problem is that how would you identify the papers which uses this technology? Really hard thing that you might find when you're reading a paper. So when you see these references, you know which all papers were used to create, but we don't know which all papers creates things uses this attention technology. So that's where we can use the sites like Semantic Scholars and connected papers. So here is the graph for attention is all you need, and this is the paper, the encoder decoder with attention mechanism we talked about. You could verify papers or new fields and the derivative. That's the thing.
All right, this is good. Just a small comment. The first time I heard about attention was actually last year after my internship was done. My mentor was saying, you guys should check this out. For the internship, we had a problem basically. We had to make an interface where you ask your question in English and you generate the query, be it SQL or any query language. So he was suggesting of using transformers to do the translation from this one to the language. Back then, this was very intimidating. I didn't understand anything. We just left it. But yeah, I guess you're right. There is some potential here, isn't it?
Yeah, sure. So you can actually see the papers that uses this attention. So you can get idea about how can you actually embed attention into your model. There are pretty much a lot of I don't remember the papers. I may share the one in the Telegram maybe later. So you can see how transformers can be embedded into maybe existing models to improve the accuracy or entirely new fields like you just talked.
Yeah, sounds
Yeah.
good, Nathan. Sounds good.
Okay.
Okay, so thanks a lot, Nitin. You really went deep. I don't think even Hari was expecting you to take the time and patience to explain RNN, LSTM, and the foundation onwards. That's really nice of you. That's good.
Uh, that's really important. If you actually use LSTM, you'll be pretty much happy that you get a wonderful output, because in the test we actually use only small sentences. So when you actually do a
That's a
collab
problem.
notebook on LSTM, then you might think, oh, really, LSTMs are really good. Why would you need a transformer? So that's why I went through all the details to focus on why
Yeah.
transformers are actually needed.
You won't see much of a difference when you're like doing small like data sets, but like
Yeah.
becomes huge. That's when
Yeah,
becomes.
also, Nitin, how do you stay updated with the latest trends in the research industry? Like, do you daily go to Arxiv and look, or you have some sort of feed on some source?
I don't really know. I think you can obviously use Twitter to get a lot of. You can actually connect to a lot of researchers, um, and you just follow them, and they will just update you on their latest works. Um, that's one way. Twitter has a lot of information. Reddit is also one wonderful place. Also, usually the place I come would be this place, Papers. Papers is I think the standard place I would come to look for the new technologies.
Okay, papers with code.
Papers with code, yeah. Then you find one paper, you will put it into connected papers and semantic scholar to see the things that relate to it. So that's how you find paper. So you can't really just go to Arxiv and find the most wonderful paper. So for
Yeah.
example,
Yeah.
the LSTM paper was a 1997 paper. You can't find it on the Arxiv. So you should just use the citations for creating a map and then look for the papers. That's, I think, better way.
Sounds good, yeah. So, do you try implementing these papers? Like, what's your fun thing to do, or you just like reading papers in general?
I mostly look at the papers, and I like doing the maths behind it mostly. Uh, but I would really need something to write on if I needed to explain the maths. So that's why I didn't include it in the presentation. Also, the maths might be a little bit intimidating at first,
Yeah.
but I like that part of these things. But implementation, I rarely do implementation. When I have some use cases, then I might use it. That's all. I am trying to actually create a this music player for Android, which can actually help you separate out the karaoke and also different instruments. There are some models that exist for it.
Yeah, I
So I'm
found a
trying.
paper on that similar. I think I have it.
Yeah, do share it.
And yeah, I'll share it with you. Because I came across this, I was like planning on getting into audio. Like for me, even I have the similar process. Like I just read some, like I just find something interesting on Twitter. I just read it, go through it,
Yeah.
and maybe like just skim through it. And maybe like whenever I'm in that use case, I just go to connected papers and like find out papers that I actually need. So shall we stop the live stream?
Yeah, yeah, of course, we can stop the live stream and then we can slowly wind up. Yeah.
Yeah.